So we now transition to convex halls. In so doing, we also move from the confines of polygons to point sets, so sort of arbitrary collections of points in space. So we have a bit more freedom than before, but polygons will still actually play a pretty big role when we're dealing with the analysis and the algorithms that dissect the properties of points in the plane and points in 3 dimensions. And convex halls are really one of the arguably the most fundamental concepts in algorithms in computational geometry. If you take an algorithms class, even if you don't have a huge background in computational geometry, you'll immediately think about convex halls if someone talks to you about or asks you about computational geometry. So in terms of convexity, because that's a sort of a fundamental component of convex halls, what we generally mean is a region where any 2 points are visible to each other within that region. So again, this is one of those cases where I think you sort of know it when you see it, at least for smaller, for smaller boundaries, because you'll see a sort of fairly obvious invagination where 2 points wouldn't be able to see each other. You wouldn't be able to draw a diagonal between them without leaving the polygon if it weren't convex. Now, formally, the convex hall is the smallest such region around a point set, or it's also considered the intersection of all convex sets, which I don't find a hugely intuitive or useful definition, but that is the sort of formal way to state it. But actually, probably the most intuitive way to understand the convex hall is effectively as an elastic band around a set of nails on a board, or if you go back to this sort of kindergarten example with a geoboard, we take these elastics and you basically wrap them around data points in a grid. Well, the convex hall is basically just that. It's just an elastic band tightly wrapped around your data set. So the convex hall of this entire geoboard would basically be an elastic band that wraps around the entire board. So that's a good sort of, at least in the 2-dimensional case, a good way to sort of intuitively think about, does this look like a convex hall when you're calculating it? Now in this case, I think it's actually really helpful to jump right in with an example using the Python ecosystem. And we're going to start using scipy.spatial, which is super useful for doing computational geometry calculations. And it has this built-in convex hall class, which accepts a set of points. And here we're going to use a random set of 2D points, which we're using numpy to generate. So numpy.random sample, which is 35 points with x and y coordinates, so the two columns there. Feed that in, generate a Hall instance out of this class, which is initialized with these points. And then we'll actually generate the plot using scipy.spatial as well. So you can actually see that it has a built-in convex hall plot 2D function. So clearly the developers felt that convex halls are so fundamental and so important that we actually need a built-in function to facilitate their visualization in 2 dimensions. So let's run this for a few different cases. So these are random data sets. In all of these cases, the code is executing just fine. We have different sets of points, and we're still getting the convex hall. And from a sort of visual inspection standpoint, it's pretty much what you'd expect. It's like an elastic band that wraps around all the points on the inside, as such. Now, when you're generating a random set of data points, you're effectively always guaranteed that those points meet a certain criterion called general position. Now, in the plane, basically a set of points are said to be in general position if they avoid degenerate situations. So one obvious degenerate situation is you have multiple data points, or at least 2, that share the exact same x and y coordinates. Then you have redundant data, and how does the algorithm deal with that? The precise definition varies depending on the algorithm. So there are certain algorithms that are susceptible to certain types of degeneracies. But in this case, I'll often use random sets of data as input for examples for this very reason, so just to avoid, real-world data sets are often in such a state that they require curation before you can apply a computational geometry algorithm to them, and it's just really useful for you to know that and to realize that just because you're getting an error or the algorithm isn't working doesn't mean that the data is completely incorrect. It just means that there may be 1 or 2 issues that needs to be cleaned up. There might be redundant points, or there's points that are just a little bit too close together, so that if they're within 9 decimal places at effectively the same position, the algorithm might have floating point problems during the calculation. So it's just something to be aware of. So here I've produced an example of a degenerate point set. So another classic example of degeneracy is basically collinear points. So if 3 or more points are collinear, that can actually cause quite a few issues in certain algorithms. And certainly for the convex hull, it would typically cause issues, and I actually thought this was going to be a really nice example. So using scipy.spatial.convex hull, where it would fail because the input data set has collinear points at the top and the bottom here. But you can actually see that both the code proper and the plotting code had no problem drawing the convex hull for this data set with degenerate vertices. Now, the reason for this is because the underlying library, so scipy.spatial.convex hull, is actually basically an API. It's a wrapper for the QHull library, which is one of the two major sort of low-level, very fast, very high-performance, and very sort of very well-tested libraries to do computational geometry that are out there. So it basically leverages the sort of really smart code written in that particular library, and that code is actually capable of filtering out the problematic points in this case. And if you specify a special QHull option, in this case it's QC, there are other flags for QHull that will give you different information back. You don't normally have to use these flags, but in this case I was curious as to why this worked, because I was actually trying to design an example that would fail because the input data was not in general position. If you want to pull that information out, certain special categories of information require extra flags to QHull, as shown here. And so actually we can pull out the indices of the violating data points and the indices of their neighbors, I think it is. Yeah, that's what I've written here. So if you use this XQC option, it'll tell you what the violating indices are. Because otherwise, how would the algorithm decide which of these points are needed to form the boundary? So would you, for example, just connect this point here with this point here, or would you calculate the point on the far left with this one here, but then skip this one here, but have to use this one here? So that sort of degeneracy situation is often not properly handled by algorithms. But in this case, you can see that the sort of input data checking is smart enough, it's sophisticated enough to actually filter out that information. But it's important to realize that if you're dealing with another piece of software or you're writing your own, handling general position exceptions and this sort of thing can actually be a fairly important consideration in certain circumstances. Now, the convex hull also introduces the really important need to understand how long it takes to run a particular algorithm on a computer. This is because even for many common real-world use cases, as you go from, say, 10 data points to 1,000 data points, you can talk about an order of magnitude increase in the amount of time it takes to run the calculation. If you move up to, say, 100,000 or 1 million or 10 million data points, you could be talking about the difference between an hour and a week in computation time, and that can be a pretty big deal in terms of productivity, or in certain other cases, search and rescue situations, it actually might be really important to have a highly performant algorithm for doing computational geometry. So I'd just like to basically introduce at a sort of very intuitive level how computational geometers and computer scientists in general annotate the speed, the time complexity that a particular algorithm has. Now, many of you may have seen this, but some of you may have not, and I'm certainly not a highly specialized expert in the field of algorithm time complexity, but basically the idea is that you use big O notation. So you can see in this table here, there's these different performance time complexities, and they all have this big O notation. And then in brackets here, in the parentheses, we have the actual function that varies as a function of the number of input points, n. So here we have O, which is basically the big O notation, and then f of n, which is how much the total calculation time varies as a function of the number of input data points, n. And you'll often see the upper bound being represented as a constant times f of n. So the constant could be something like, how new is your processor, how good is your computer. That still wouldn't change, shouldn't change the time complexity of the algorithm, it'll just change the sort of absolute amount of time required. So if you have a large enough set of data points, regardless of how fast your computer is, eventually you'll run into problems with a really large number of data points if you don't have a really efficient, an algorithm with a performant time complexity that's reasonable. So the upper bound, as I mentioned here, basically means that we typically ignore the lower values of n and focus on the worst case scenario. So when is my algorithm going to stop working? So there's a few sort of classic examples here. So O of 1 is basically constant time complexity, so adding two numbers. N log n is log linear. This is actually going to pop up a lot in my talk today. It's quite common to have log linear time performance as the optimal time performance or time complexity for a computational geometry algorithm in the plane. An example of that is sorting a list. So you can't, in the worst case scenario, you can't sort a list faster than log linear. Quadratic time complexity, which is true for some of the incremental convex Hull algorithms. There's also polynomial and exponential algorithms, which are quite a bit slower. So robot arm motion planning and perhaps unsurprisingly brute force algorithms tend to perform quite slowly, so the exponential time scale. So we're going to almost entirely focus on time complexity, but there are algorithms where you have to think about the amount of physical memory, the amount of RAM that's being consumed in the computer as a result of the steps of the algorithm, so the space complexity of the algorithm. Now in practice, measuring space complexity, at least in my hands, is a lot more difficult than empirically measuring the time complexity. And for sort of hardcore computer scientists, you should actually be able to just look at the code without doing empirical measurements and actually reduce the sort of each step in the algorithm to a specific well-known operation for which the time complexity is known, and then figure out what the time-limiting step is. And that time-limiting step will tell you what big O notation applies to that particular overall algorithm. But for our purposes, I thought it would be useful to take a more sort of empirical approach and just calculate it using the notebook. And we're going to actually estimate the time complexity of the SciPy spatial convex Hull algorithm, which is of course just a wrapper, an API to the C language QHull package. So I basically have a number of different random sets of data points. So it's going to be up to 1 million data points here. And we're going to basically generate a random set of points in the plane. So we're just dealing with the plane here, and just very crudely doing a single measurement at each number of data points using SciPy spatial convex Hull to generate the Hull instance. And that will, just generating the Hull instance actually runs the calculation. And we'll just rerun this code. Of course, the numbers will vary depending on your machine, but the general growth pattern, the big O notation behavior should be roughly the same as mine for that particular algorithm and that particular code. So we're using SciPy to basically curve fit these data points using the nonlinear fitting here. So curve fit, we have basically a linear function, a log linear function, a quadratic function that we're fitting the number of data points with basically constants, so a cofactor m and a constant c, which are sort of the idiosyncrasies of your particular computer factoring into the empirical measurement. And if we look at the results here, run it again just to see if they look the same, and they look pretty similar. Certainly quadratic time complexity doesn't seem to apply. It looks like it's either one of linear or log linear. And if you're reasonably familiar with the literature, and if you've read the textbook, then you'll know that log linear is effectively the theoretical performance limit. So it looks like SciPy spatial convex Hull in the two-dimensional context is performing as well as it can. The Python community is not in a position to make this algorithm any faster. I mean, you could write the code so that on a given machine it might operate a little more quickly, but the actual algorithm and the growth rate in terms of the amount of time it takes as a function of input data points is already the best that it can be from a theoretical standpoint. So QHull, which is the code that's ultimately running the code above, uses the QuickHull algorithm, which was published only about 20 years ago, actually. So a lot of the algorithms that we use even now are from the last 10, 20 years, because computational geometry is quite young. And it actually has output-sensitive format, so depending on the number, the percentage of points in your input data that are on the convex Hull and not on the convex Hull, the performance of the algorithm can improve in some cases to be actually a little bit faster than log linear. So I just made a table here which summarizes for some of the more straightforward algorithms the time complexities in two-dimensional space and also in three-dimensional space. In some cases you can see it's the same. So for incremental, even though it's quadratic time complexity, which isn't optimal, it's often implemented just because of conceptual simplicity. And that's something I sort of experience a lot. So if I for whatever reason have to write my own computational geometry algorithm, it's often true that I'll go for the one that's easiest to implement, even if it's not the optimal time complexity, just because I know how much time can go into trying to implement the much more complex algorithms. Of course, there's also something to be said for the sort of open source community effort to implement the optimal algorithm so that every person doesn't have to sort of reinvent the wheel and work with a much slower algorithm just because they don't have the time to invest to generate the much faster working code. This gift wrapping algorithm is kind of interesting in the sense that it's also input sensitive, or actually output sensitive, since the number of points that end up on the hull determines how long it takes to run the calculation. And same thing in 3D, except in this case we're talking about the number of points on the face of the polyhedron for the convex hull. So in the 3 dimensions, the convex hull is more like a sort of like a plastic bag wrapping around the data set. So gram scan, this one is optimal, but doesn't extend to 3D, and then the divide and conquer, this does extend to 3D, and its time complexity is optimal in both dimensions. But as you can see, in 4 dimensions or higher, it has a somewhat different time complexity. So as I mentioned, yes, the Python community really can't do better in terms of the actual algorithm that's being used for SciPy to spatial to convex hull. Rather than just taking my word for it, I thought I'd take this amazing example that I found in the textbook and just sort of demonstrate it using Python code, just producing a simple plot that shows that for this parabolic data set, so we have basically y equals x squared as the function, and just scattering about 12 different data points here, going from 0 up to 11 here, and then basically calculating I'm just plotting the polygon in this case, but you can imagine that effectively, if you want to calculate the convex hull of this system, all you have to do is sort the data points, right? So once we know the order, going from the smallest x value to largest x value, we've connected all of the data points from the convex hull. So we effectively calculated the convex hull. But that means that the sorting operation is effectively we can't go faster than that because this is fundamentally being reduced to a sorting operation. And it turns out that even if we didn't care about the order and we only wanted to identify the points, we still couldn't go faster than log linear. So sorting can't be done more quickly than log linear in the worst case scenario. So that's how we basically intuitively argue that the theoretical limit for the convex hull algorithm is log linear. But even if we didn't need the order of the points of the convex hull, about 20 years ago, well 30 years ago now, Franco Preparata and Michael Shamos had finally proven that even if you don't need the order of the points, log linear is still the best that we can do. So I hope that makes sense. So basically, if you sort the points, you get the convex hull. So we've kind of reduced the problem to an even simpler problem, which is sorting. And that tells us that we effectively have a sorting problem in the simplest case, and even that simplest case is log linear time complexity. So I thought we'd now move on to some practical examples. This is, after all, an interactive tutorial, and convex hull is one of the most useful, one of the most famous and fundamental algorithms and concepts to calculate in computational geometry, so it makes sense that we would do two examples, one in 2 dimensions and then one in 3 dimensions, of using the Python ecosystem to calculate this particular property of a point set. So let's start off with a specific problem, which I've just sort of cooked up. So let's say you have a startup, it's a robotic startup, and what you basically want to do as a sort of test drive is to make your land robot walk from the westernmost point of Oregon to its easternmost point of Oregon. But it turns out that the residents of Oregon don't want this robot walking through their properties or through their hiking trails, and so you've decided that you're going to use the perimeter of Oregon for the route, and you've also found out that the neighboring states are a bit friendlier about using their land. So basically the constraints on the problem are that you can walk either on the boundary of the border of Oregon, or you can walk a little bit outside of the territory, so in a neighboring state. So the first thing I wanted to do in this problem was basically sensibly identify the start and end points, the western and easternmost points. So I just use the very useful numpy to argmin and numpy to argmax to pull out the indices of basically the minimum and maximum value of the x-coordinate for all of the border coordinates for Oregon. So we have 0 and 137 as those two indices. So we pull out those coordinates, and I'm just going to plot them here because if you're working with a large number of data points, and there's around 200 of these for the Oregon border, it's often worth your time to you spend 2 or 3 minutes plotting the data and save yourself 2 or 3 hours if you didn't plot the data because you had the wrong start and end points. I think it's almost always worth your time to plot, especially when you're first tackling a problem, to plot the data and make sure that it makes sense, that yes, indeed, it looks like you have the westernmost point and the easternmost point properly identified. So now we're actually going to do the core of the work, which is basically calculating the Euclidean distance if we were just to follow the border. So basically this is border path 1 going clockwise and border path 2 going counterclockwise from the westernmost to easternmost points. And to calculate those distances, I think what I've done here is effectively, I've done a distance matrix between basically the data from the start to the end, and then from the second point to the end, and effectively you're basically just calculating the Euclidean distance between each point and summing those together, as you can see at the end here, for both the clockwise and the counterclockwise distances. And now we're also using the convex hull to calculate the convex hull-based routes, so we're comparing walking directly on the border with actually walking on the convex hull itself, which is a little bit outside the border because it's enclosing all of the points in the convex region. And then again, we're summing together the Euclidean distances in a similar fashion for the convex hull values. You're calculating your distance matrix here from the start to the second last index, and then from the second index to the actual last index, and summing all of those individual Euclidean distances together. And I'm not sure you'd necessarily expect this result. So actually it turns out that walking on the border in either direction is actually a longer route than following the convex hull, even though the convex hull encloses all of the data points that are within the border. And it turns out that following hull path 1 gives you the shortest distance. So granted, this distance hasn't been converted to kilometers or miles. We'd have to sort of use a scale-based distance conversion, but it's already clear here that hull path 1 is the fastest route for our autonomous robot. Now, it could be that actually this route would take the robot into the Pacific Ocean, but for the purposes of this problem, let's just ignore that particular fact and just sort of try to take from the solution that actually it's quite useful from the perspective of robot motion planning to calculate the convex hull of a potential obstruction. In this case, it's the entire state of Oregon, but it could be anything like a tree or a specific set of coordinates for a region that you want to avoid. And you have the convex hull as a sort of tool for assessing sort of 2 or more possible paths around that obstruction, which are actually turning out to be the sort of the shortest Euclidean distance traversed by your particular object around the obstruction. So clockwise hull path 1 is the shortest in this particular case. So if we now move on to the 3-dimensional case, and this case is actually one from my own research, so a little bit shameless, but actually I think you'll find that this is also really interesting usage of computational geometry for tackling a really important biological problem, which is the spherical influenza A virus, which causes thousands and thousands of illnesses each year in humans during the winter season in temperate climates. So I started off by just loading in the coordinates. So I've taken the the atomic coordinates are the coordinates of basically all of the atoms on the outer surface of the virus. So the virus has this protective layer of fat molecules, basically. I've taken basically one coordinate per molecule on the surface, and use that to represent those protective molecules. So now we have x, y, and z coordinates. This is a three-dimensional problem. I'm just plotting them to just show you that the data is in fact roughly spherical. It's not perfectly spherical, but certainly it should be clear that we have a roughly spherical set of input coordinates. And so what we want to do is actually, conceptually it seems like a fairly straightforward thing to do. We just want to calculate the surface area of this virus. Now, because it's roughly spherical, you could argue that maybe you should just treat it as a sphere and estimate its radius, but perhaps we want to be actually a fair bit more accurate than that because it's not a perfect sphere. So we'll actually go ahead and calculate the convex hull of this three-dimensional virus. So again, we're using scpi.spatial.convex hull as a function of the input generator, so the input flu coordinates. Now, in this case, there's no built-in plotting function, so we can't just cheat and use the scip.spatial.plot convex hull 2D because we're in a 3D case. So here we're actually going to explicitly pull out the hull triangle coordinates using the instance of the convex hull class, so flu hull.points, which is just the original data points. And then we're going to index those points using the indices of the simplices. And simplices in this case is basically just a fancy word for the fundamental polygons, so the triangles that are used as the fundamental units of the convex hull. And then we'll feed them into this matplotlib poly 3D collection object. So we have effectively an array of triangles, array of triangle coordinates. Add them to the 3D collection of this matplotlib axis, and then go ahead and label the plot with the necessary details. Now it turns out, and I think this is actually a fairly recent development, that we can actually access the area of the convex hull from the instance object here, so flu hull.area. So I used to actually do this by basically summing together the polygon, every single triangle surface area using Heron's equation, but it turns out that this is actually now built into scip.spatial.convex hull, which is again probably leveraging the functionality from the underlying Q hull code. And I also thought it would be useful just to check, or just to compare the surface area that we calculate by reconstituting the surface with triangles with the surface area of a roughly equivalent sphere. So I've estimated the radius of this roughly equivalent sphere by taking the difference of the maximum and minimum z coordinates and dividing that by 2. So basically dividing a rough estimate of the diameter by 2. There's probably more accurate ways to do this, like taking the average radius from the centroid of the system for all of the molecules. But for our purposes, we just want to see if it's roughly what we'd expect. And as you can see here, it's about 97% reconstitution, and indeed there are a number of sort of invaginations on the surface of the virus. So this is actually, it looks like it's a really good estimation of it's a really good indicator that we're in the right ballpark for estimating the surface area of a virus. So just using the built-in tools that are already available in the Python ecosystem, scipy.spatial.convex hull, we've now actually solved a really interesting biophysical problem, which is what is the surface area of these viruses that cause severe human illness and death every year in the world. So I hope that sort of resonates with you, that actually developing these tools can have a really real impact on scientific endeavors.